We are going to talk about trigonometric functions of angles. So we have, in the previous ones, we have defined trig ratios for acute angles. And here we're going to extend the trig ratios to all angles by defining the trig functions of angles. And this way we can solve practical problems that involve angles that are not acute. So they can be any type of angle. So we're always going to place theta in standard position so that our point PXY is a point on the terminal side of theta. And in this triangle, the opposite side has the length of y. The adjacent side will have the length of x. And then our r will be the hypotenuse. We can use the Pythagorean Theorem. We can see that the hypotenuse is the distance from this point to that point. So it's going to have the distance of a squared plus b squared equals c squared. In this case, it'll be x squared plus y squared equals r squared. So r, if we take the square root of both sides, we get r is equal to the square root of x squared plus y squared. So now we can understand that it's still, sine is still the opposite over the hypotenuse, but instead we're going to see that sine is y over r. Cosine would be x over r. Tangent would be y over x, and then the reciprocals are the same way. Understanding that our denominators cannot be equal to 0. The value of trig functions do not depend on the choice of the point, because if our point PXY is any other point on the terminal side of the triangle, they're going to be similar. So the terminal side of this is always going to be positive from O to P. Our R is, because it's a distance, you're always going to have a positive distance on there. And that's why when we took square root, we don't worry about the plus or minus part. So remembering in our signs of our trig functions, this is stuff you need to know. We've talked about this before, that quadrant 1, everything is positive. Quadrant 2, sine and cosecant will be positive. Quadrant 3, it'll be tangent and cotangent. And quadrant 4, cosine and secant will be positive. It's because of the x and y values. And we talked about all students take calculus, because to remember that. So this would be all sine, the tangent, and the cosines. And then, of course, the reciprocal identities go with them. All right, so let's go and do some problems. So we are going to find the trig functions of some angles. So we want to find the cosine of 135 degrees. So we are looking at understanding a couple of things about this. So if we're looking at 135 degrees, I'm going to pull out my unit circle handout. 135 degrees, that lands us in quadrant 2. We need to be able to know that. Remember, it's up to 180 for the top half. Halfway up would be 90, so we know it's between 90 and 180. That tells us we're into quadrant 2. So quadrant 2 helps us know our sine. So quadrant 2. And we know that in quadrant 2, cosine will be negative. And we can use what we do know. So let's take 180 minus 135 degrees. That'll get us 45 degrees. And we've talked about this before, where we can use that value of the shortest distance to the closest x-axis, which would be our 45 degrees, And we can use what we know about a 45-degree angle in our unit circle, that we know that the value is going to be the square root of 2 over 2 for our cosine right here. So going back to our unit circle, you really want to know those. So we know that our cosine values will be x over r, but because it's in quadrant 2, it will be negative. And we know that the cosine of 45 degrees is the square root of 2 over 2. So we know that this will be negative the square root of 2 over 2. So we can use our prior knowledge from our unit circle to help us understand what we're doing. All right, let's go find another one. Let's find the tangent of 390 degrees. So let me go back here for just a second and let's review our reference angles. So if we're letting theta be an angle in standard position, that reference angle, again, is the closest way to your x-axis. In case you weren't here for the last time we talked about this, we called it t bar was the distance, but we're looking at theta bar for the reference angle. So we can use that same part there to figure out what we are looking for. So we just did one where we were over here in this quadrant, so we can use this angle to help us so that we can better understand the values without having to always pull out our calculator, knowing our values from our unit circle. So if you end up over in quadrant 3, you're just going to do this short distance. Quadrant 4. Quadrant 3, we're going to use that short distance there, because that reference angle will help us know what we need to know. So we're looking at tangent of 390, so let's talk about what quadrant we think that's going to be in. Remember, on our unit circle, we're going to hit 90 up here, 180, it'll be 270 to 360. This is between this is past 360, so we're actually back up into quadrant 1. So let's go look at that for a second. 360 would be all the way around and then another 30. So we'd be back into quadrant 1 for this. So we can take 390 minus 360 gets us 30 degrees. So we can use the tangent of 30 degrees. And tangent is going to be y over x. And we know that the tangent, or the value for 30 degrees, our y is going to be 1/2. Our x is square root of 3 over 2. So 1/2 over the square root of 3 over 2. So we don't divide by fractions, we multiply by reciprocals. So 1/2 times 2 over the square root of 3 will get us 1 over the square root of 3. Rationalizing the denominators will get us the square root of 3, and square root of 3 times square root of 3 is square root of 9. Square root of 9 is 3. So we can understand, and this will be positive because we're back into quadrant 1, that the tangent of 390 degrees would be equal to the square root of 3 over 3. And that would be your answer. All right, let's go find some actual reference angles. So this was finding the value, but kind of using that same procedure. Let's go actually find the reference angle. So we were using the distances to get back before, and that way we can use those angles. We're actually just going to find some angles. So if we're looking at theta is equal to 5 pi over 3. So again, if we're looking at our unit circle, where do we land with 5 pi over 3? So if we're looking again at our circle, and I'm just going to draw us a unit circle here. So 5 pi over 3, that would get us 3 pi over 3 would be over to here, right? That's 1 pi. Same denominator, 3 pi over 3. And then we'd land about, it's thirds, so this would be like 4 pi over 3 and 5 pi over 3. So we can use that same process without even having our unit circle diagram, because it's broken up into thirds for each pi. So this would be like 1 pi, 2 pi, 3 pi, 4 pi, 5 pi over 3. And we can see on the unit circle, that's about where we land. Now, we need to find our theta bar. So if we take 2 pi, because 2 pi would be full around, and we can say that 2 pi, we need a common denominator, so that'll get us 6 pi over 3 is the same as 2 pi. And then we can subtract out 5 pi over 3. That'll get us 1 pi over 3. So that would be our reference angle right there. All right, let's look at another one. What about if we have theta is equal to 870 degrees? Well, we know it's 360 all the way around, so let's draw another circle here. So 360 would get us once around. Another 360 takes us to 720, gets us another around. And then we're going to have some more that's going to land us over into here. So we can take 870 minus twice around is 720, or you can do 360s at a time. It doesn't matter. So 720 will leave us with a 150 degree angle. So our theta bar is equal to 180, because our closest distance is right there, minus 150 degrees. So our reference angle will be 30. All right. We are going to use our reference angles to evaluate some trig functions. So to find the values of trig functions for any angle theta, we carry out the following steps. We'll find the reference angle theta bar associated with the angle, determine the sign of the trig function by noting the quadrant, and then the value of the trig function of theta is the same, except possibly for the sign, as the value of the trig function of theta bar. All right, so we're going to use everything we've been using and a little bit more. So we are looking at using that reference angle to figure out some information. So we're going to look at using the reference angle to evaluate trig functions. That way you know for sure what we're doing here. So if we're looking at the sine of 240 degrees, what quadrant is that in? Well, we know that 180 gets us halfway around, and 270 is at the bottom of our circle. So again, 180 and then 270. So we can use those values to understand it's going to be in quadrant 3. So we're in quadrant 3, because that we need to find the value. So because we're in quadrant 3, we got to end up at the closest x-axis up here. So in quadrant 3, we're going to come back to this one. So we're going to take 240 minus 180 to find our reference angle, and that'll get us 60 degrees. So the sine of 240 degrees would be equal to the sine of 60 degrees, but we need to decide if this is positive or negative. Well, in quadrant 3, the only things that are positive are tangent and cotangent, so we know it will be negative, the sine of 60 degrees. And from our unit circle, we know that the sine of 60 degrees is the square root of 3 over 2, and we'll attach that negative sign. So again, I'm telling you, we're going to use these a lot. You need to know what these values are because it will make things a lot easier for you. And that would be your answer. All right, let's go find the cotangent of 495 degrees. Well, 495 degrees is greater than going around our whole circle. So let's take 495 minus 360 degrees. Well, that gets us 135 degrees. And 135 is greater than 90 but less than 180, so that tells us we're going to land in quadrant 2. So our theta bar would be equal to, the closest x-axis is going to be at that 180 again, but we're up in this quadrant, 180 minus 135 degrees will get us 45 degrees. Now, we're in quadrant 2, so we know that cotangent will be negative. So we know that the cotangent of 495 degrees is equal to the cotangent of 135 degrees, which will be equal to the cotangent of 45 degrees, except that the cotangent of 45 would be positive, so we need to tack on that negative sign. And we know that the cotangent of 45, we've got to put in some values. We know that the reference point for that would be the square root of 2 over 2, square root of 2 over 2, but our x will be negative in our quadrant 2. So we have to do a little bit of work here. So we'll have cotangent is x over our y, so it'll be negative square root of 2 over 2 divided by the square root of 2 over 2. And then they're the same thing on top of each other, so we just know it's going to be negative 1. And that would be our answer. All right, let's go look at another angle. So we are looking at the sine of 16 pi over 3. Well, that's way more than 2 pi, because 2 pi would be 6 pi over 3. So let's take out once around. That would be a whole circle. So we'll take out 2 pi, and we end up with 10 pi over 3. Well, that's still greater than a whole unit circle. So let's take out another 6 pi over 3. So this is just taking out 2 pi, which is around our whole circle. And we end up with 4 pi over 3. Well, 4 pi over 3 is going to land us in quadrant 3, because if we think about our unit circle, halfway around would be 3 pi over 3, because that's 1 pi. One more would be 4 pi over 3. And we can see for sure it's that way, but it's understanding the concept of it. And so that's going to land us into quadrant 3. We're dealing with sine, and we know that sine will be negative in our quadrant 3. Our theta bar, we need to go back up to our closest x-axis, which would be pi. So we need to take our 4 pi over 3, and we need to take out pi. But again, we need to have a common denominator of 3. So 3 pi over 3 is the same thing as pi. And that'll leave us with pi over 3. So now we can say that the sine of 16 pi over 3 is equal to the sine of 4 pi over 3, which will be equal to the negative of pi over 3, so negative of sine of pi over 3, and the sine of pi over 3 from our unit circle is square root of 3 over 2 and we still have that negative. And just to clarify for you guys, we've talked about coterminating. We've found some angles before where they stop at the same point. And all of these angles that we're looking at, they coterminate with each other. So 16 pi over 3 will coterminate with the sine of 4 pi over 3. It doesn't coterminate with this one. But when you're finding that angle after taking away a couple of them, it's coterminating, means it stops at the same point. So using some of our vocabulary that we've already talked about sometimes can be useful. All right, let's go find another one. So we are going to find the secant of negative pi over 4. Well, now when it's a negative value, we know we're going to go from our standard angle on our circle, we're going to come down. So we know it's going to land us into quadrant 4, because we're going to start from there and go down. Well, the terminal angle for that, our theta bar, is going to be equal to that same distance back up, which will just be pi over 4. Because you're just going right back to where you started from the standard position. So we know that the secant of negative pi over 4 will be equal to the secant of pi over 4. And is it going to be positive or negative? Well, because we're in quadrant 4 and secant goes with cosine, it's an x value. And so even though we're in quadrant 4 or quadrant 1, it's still the x values will be positive because we're on the positive side of the x axis there. And so we know that it's going to be a positive one, so it'll just be equal to it. So secant is positive, just to clarify. And so it's going to be the reciprocal of our value for cosine. And for pi over 4, we know that our terminal point is square root of 2 over 2, square root of 2 over 2, but we only need the x value. So it'll be 1 over that square root of 2 over 2. Again, we don't divide by fractions, we multiply by reciprocals. So the 1, we're just going to multiply it by 1. So the 1 doesn't matter, so we end up with 2 over the square root of 2. Rationalizing our denominator, we get 2 square roots of 2 over 2, because square root of 2 times square root of 2, square root of 4 gets us 2. And then the 2's will reduce, we'll end up with the square root of 2 as our final value of our function. All right, so if you recall from our unit circle, so on our unit circle, we know that x squared plus y squared was equal to 1, but now we can say that x squared plus y squared is equal to r squared. So that's a little bit different of what we have been looking for. So we are going back to expressing one trig function in terms of another one. We've done this before, and this is important for you to understand because we need to make sure that we can do everything that we need to do and that we can build our way up to the trig identities. Everything that we learn builds upon itself. So we know that sine squared theta plus cosine squared theta, what is it going to look like? We know that it would have been equal to 1, but let's actually look at this. So we know that sine squared is now y over r, quantity squared, plus cosine would be x over r squared. Well, that would be y squared over r squared plus x squared over r squared, just squaring each of our values. We can put this over the same denominator, so we get y squared plus x squared over r squared. Well, x squared plus y squared, oh, that's right up here. It's equal to r squared. So now we're just substituting this for this r squared. R squared over r squared is still equal to 1. So I'm just showing you that even though we're using r squared now, it's still the same process. And we still can use that same equation so that you know that not a whole lot has changed. There's just been a few things. All right, so we're going to go back and express sine theta in terms of cosine theta. So remember, we have our sine theta, or our sine squared theta, plus cosine squared theta is equal to 1. If I want to do sine in terms of cosine, I need to solve for sine. So I'm going to subtract my cosine squared theta from both sides and get sine squared theta equal to 1 minus cosine squared theta. Taking the square root of both sides, we get sine theta is equal to plus or minus the square root of 1 minus cosine squared theta. And we know it's plus or minus because it all depends on, whenever you introduce the radical, you have to do that. And this is going to depend on what quadrant you're in. So if you're in quadrant 1 and 2, it would be positive because that's what our sine is. If it was in quadrant 3 or 4, it would be negative because that's where sine is negative. So what we're going to do next is to express, and you decide that by the sine, not the cosine. We're going to express tangent theta in terms of sine theta. And we're told that we're in quadrant 2. All right, so let's start with our tangent theta. Tangent theta is equal to sine theta over our cosine theta. And using our part that we just went over, I'm going to go back over it again. So we have sine squared theta plus our cosine squared theta is equal to 1. I want to just do it in terms of sine. So I need cosine to become in terms of sine. So it's opposite of what we did up here. So I need to solve for cosine. So I'm going to subtract my sine squared theta from both sides. And I end up with cosine squared theta is equal to 1 minus sine squared theta. Taking the square root of both sides, we end up with cosine theta is equal to plus or minus the square root of 1 minus sine squared theta. Now we're in quadrant 2, and in quadrant 2 we know that cosine is negative. So because of that, I know that cosine theta will be equal to the negative of the square root of 1 minus sine squared theta. So we're deciding this by what cosine is. Has nothing to do with sine at that point. So now I can take this and rewrite tangent theta is equal to sine theta divided by the negative of the square root of 1 minus sine squared theta. And this would be writing tangent in terms of sine according to quadrant 2. These are important to understand because when we get into identities, this is going to help you understand what you're doing with those. That's a little ways down the road, but we will get there. All right, so the next one that we're going to look at is to evaluate a trig function. So we're going to evaluate a trig function, and we are looking at a couple of things that we're told. So if tangent theta is equal to 2/3 and theta is in quadrant 3, we want to find cosine of theta. So what we need to do is we need to write cosine theta in terms of tangent theta. So how are we going to do that? Well, this is getting a little bit into our identities. If we remember our trig identities, we have a trig identity that is that tangent squared theta plus 1 was equal to secant squared theta. And this can help us because we know that secant is the reciprocal identity of cosine. So that's where we can use this to get where we need to be. So we can solve for secant, so we can take the square root of both sides and get that secant theta is equal to plus or minus that square root of tangent squared theta plus 1. But we were told we're in quadrant 3. So in quadrant 3, secant, which is cosine, will be negative, well, the 1 over cosine. So secant is negative. So I'm going to kind of flip this. So it'll be secant theta is equal to negative the square root of tangent squared theta plus 1. Now we need to actually find cosine. So cosine theta would be equal to 1 over secant theta, which would be equal to 1 over that negative square root of tangent squared theta plus 1. So that's where we can use that identity to figure out what we need. So that means our cosine theta would be equal to 1 over the negative of the square root of 2/3 squared, because that's what our tangent theta is equal to, plus 1. So that's equal to 1 over the negative 2/3 squared. Well, that would be 4 over 9. I'm going to change my 1 to have a common denominator, so plus 9 over 9. So that'll get us 1 over negative square root. 9 plus 4 would be 13 over 9. And then I can rewrite this as two separate radicals. So 1 over negative square root of 13 over the square root of 9. So that'll equal 1 over, let me scooch over, the negative of square root of 13 over 3. Gets us a little more simplified. All right, so now that we've got that, remember we don't divide by fractions, we multiply by reciprocals. So we don't have to show multiplying by the 1 because it doesn't change anything, but the reciprocal of this would be negative 3 over the square root of 13. And we got to rationalize our denominator, so square root of 13 over the square root of 13. So negative 3 square roots of 13 over 13. And that would be our final answer. So that's one of our more complicated type of things where you have to figure out how am I going to take tangent and make it into that. You can't, let me just clarify, you can't just say this is x over y, because what you don't know that happened is that the r canceled out. Our r values canceled. So that's why you can't just say, well, the sine would be 2 and the cosine would be 3, because we have a length of r going on, because it's not all 1 at this point. And so that's where you have to do this kind of work in order to find out what that r value is, to figure out what the whole thing is. So that's basically what we're looking at, is you can't just, this is the reduced version of things. It's not just being able to look at it and go, oh, well, isn't that x over y? Not quite. Alrighty, so let's go evaluate a trig function. All right, let's get to the next problem. So we want to evaluate some trig functions. And when we're doing that, we're going to look at if secant theta is equal to 2 in quadrant 4. We want to find the other 5 trig functions. So from 1, we want to find the rest. So understand that our secant theta is equal to the hypotenuse over the adjacent. So that means it's going to be 2 over 1. So let's draw a circle, or not a circle, a triangle in standard position. And we're still in 2 right triangles. And here's our theta. So the adjacent side would be 1, the hypotenuse is 2. We need to find the value of this other part. And to do that, we're going to use our Pythagorean theorem. So a squared plus b squared equals c squared. So it doesn't matter which side you put as a and b. We're going to put in this one as 1 squared plus b squared equals our c squared, which is 2 squared. So 1 plus b squared equals 4. Subtract the 1. We get b squared is equal to 3, square root of both sides. You get b is equal to square root of 3. It is going to be positive because it is a distance. So square root of 3 we now have right there. So now that we've got that square root of 3, we are going to look at finding our other 6 trig values, functions from there. So we have secant, we need to find sine. So remember that the sine of theta is equal to the opposite over the hypotenuse. So it'll be the square root of 3 over 2. And cosine of theta would be equal to the adjacent over the hypotenuse. And yes, it would also be the reciprocal of secant, but we want to find it using, we want to practice all of our skills, not just the reciprocals. So that's going to be 1 over 2, which is 1/2. And then tangent theta would be equal to the opposite over the adjacent, which would be the square root of 3 over 1, which is just the square root of 3. Now we already know what secant is. We need to find cosecant. So cosecant theta would be equal to the hypotenuse over the opposite. And so the hypotenuse is 2 over the opposite side is going to be the square root of 3. Rationalizing, we end up with, I'll put it down here, we have 2 square roots of 3 over 3. And then we still need to find our cotangent. So for cotangent, I'll come down here. So cotangent theta is going to be equal to the adjacent over the opposite. The adjacent will be 1 over the opposite, square root of 3. And we have to rationalize, so square root of 3 over square root of 3 gets us the square root of 3 over 3. So that's using all of the things we've been learning. We've got our SOHCAHTOA we're using and figuring out how to do that. So we have another problem here. We're going to find the area of a triangle. So the area of a triangle is 1/2 base times height, where the base is equal to our A down here, and H, the height, is equal to B sine theta. So this would be the part you need to know. So acute angles use the angle theta. Not acute angles will use 180 minus our theta. So the area of a triangle with sides of length A and B, which include angle theta, is going to be equal to 1/2 A times B sine theta, because they're telling us that the A will be our base and the height will be B times sine theta. So using that formula right there, we are going to find the area of a triangle. So let's get another piece of paper. So if we've got a triangle, and understand when I draw things, they don't always, I draw things, it doesn't always look exactly as it should. So, like you're like, well, that doesn't look like it's that angle. We're just sketching, and so it's not always going to look exactly like it would if I was trying to be perfect in this. So we are going to state that this angle, even though it looks kind of like a right triangle, it's actually 120 degrees. And you're going to go by the measurements I tell you and not how it looks. And again, we have A, and we have, so we've got our angle C, and we'll call this B. And then we are told that this is 10 centimeters, and this one is 3 centimeters. And the area is equal to 1/2 A times B sine theta. Now, it's not always going to match exactly where you're at, because I have put angle A here. So my little a is actually up here. And it's all multiplication, so it doesn't really matter. But my B is actually the part that's down here. So it's actually B A sine theta. So just be aware that you're using all of the sides, but because I labeled it differently, just so you understand, it's not always going to be exactly. It means you're going to have this times your B sine theta. All right, so the area would be equal to 1/2 times the 10 times the 3 times sine of 120 degrees. Well, if we kind of simplify this out a little bit, because we are able to do some math, so 1/2 times 10 times 3 would be 10 times 3 would be 30 divided by 2, gets us 15 of the sine 120 degrees. Now, we're going to use some of the skills we've learned. We're going to use a reference angle. So our reference angle for 120 degrees would be 60 degrees, because it's the, if we're looking at 120 gets us to here, and here is our reference angle from 180 minus 120. So we can do this off to the side for the reference angle. We'd have 180 minus 120 equals 60 degrees. So this would be equal to, and we're doing sine, it's positive in quadrant 2, so we don't have to worry about a negative sign. 15 times the sine of 60 degrees. We know the sine of 60 degrees because we've been practicing our unit circle values. Square root of 3 over 2. And that'll end up being 13 centimeters squared because we multiplied centimeters times centimeters. So that is pulling in some of the things that we've already learned in this section to making sure that we know everything we need to and we can use those skills.